In this video, we're going to introduce truth tables and look at the validity of compound and simple statements using those truth tables. So we're going to construct a truth table for a compound statement, determine whether two statements are equivalent using a truth table, and then talk about De Morgan's laws and the negation of statements, these compound statements that we've introduced. So now that we have this symbolic language to represent all of these statements, we can use these truth tables and using this simple symbology to assess the validity of these statements quickly. We can look at a lot of information at one time using these truth tables. So a truth table of a compound statement is a table that gives a true-false value of each combination of individual statement values, along with the resulting values of the compound statement. So we're going to go through these simple truth tables of our basic compound statements, and then we'll get into more complicated examples later on. So let's start with the negation truth table. We're always going to start with our statements that we're looking at. In this case, you only have one statement. We're looking at just not P. So when we look at P here, we want to look at all possibilities of P, and that's going to be either true or false. And then for each of those possibilities, we're going to see what happens with the thing in the next column, in this case, not P. And not P here is just going to be the opposite of what happens to P. So when P is true, not P is false. And when P is false, not P is going to be true. So each of the rows of the truth table give us a different option for what we're going to do. This is going to be option 1 in the first row, option 2, and then each column tells us something about a compound statement. Note that a negation is a compound statement even though it only involves one simple statement. All right, so the negation just gives you the opposite value of whatever's in the first column. Let's now look at the conjunction and disjunction truth table. Remember, conjunction is the word and disjunction is looking at the word or. So this is P or Q, or P and Q. Remember, we say and is going to be this caret symbol, or is the upside down caret symbol, is V symbol. So because the conjunction and disjunction look at two different simple statements at the same time, remember P and Q here are our simple statements. We're going to look at all possibilities of these simple statements being true or false. And there are 4 in this case. You could have both be true, both be false, or one be true and the other false in both ways. So note that if there are n simple statements involved in our compound statement, then we will have 2 to the n rows of our truth table. There are 2 to the n options or rows that we're going to look at. And the way that we can kind of look at these rows is we can just say for our first statement, for like P, we're just going to go all the trues that we need. So let's say we had, if there's 2, we just do 2 trues and then 2 falses. We do all trues, then all falses. For Q, our next statement, we're just going to alternate true, false, true, false. This is a nice systematic way to make sure we get every possible option. You look at all the options where P is true, then all the options where P is false, and then kind of down the line. So since there are 2 options here, there are 2 squared, 4 options total. We'll see 3 n being 3 and 8 options later on. All right, so we have our 4 different options: true, 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 false, false, true, false, false. And now we're looking at the validity of P and Q. And note that if for P and Q to be true, both P, and then here's our keyword, and Q have to have a value of true. So we can see in our first row, both P and Q are true, so P and Q is true. The rest of them are all going to be false because there's at least one false in between P and Q. Q is false in the first, P is false in the second, and then they're both false in the third. This is our truth table for a conjunction, P and Q. Now let's think about disjunction. Again, we start with our same basic idea: true, 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 false, false, true, false, false for P and Q. But for P or Q to be true, we need either P, and then our keyword, or Q to be true, but we don't need both. So the first 3 rows of our disjunction truth table will all be true because there's a true in each of the first 3 rows. The last row will be false because both P and Q don't have any true in them. They're both false. This is our basic disjunction table. We have our conjunction table, and we're going to be looking at our conditional in a little bit later. So let's look at an example now. Under what conditions is the following statement true? I have a high school diploma, or I have a full-time job and no high school diploma. This is a compound statement involving a few simple statements. In this case, this can be broken down into 2 simple statements. P being I have a high school diploma, Q being I have a full-time job. And we could translate this sentence into some symbology. So I have a high school diploma, we say is P. We have or is our V symbol. I have a full-time job is Q. And then no high school diploma would be not P. And we combine that with the and. And then it's just a matter of having the parentheses in the right place. So P or Q and not P. So in order to think about this compound statement, we're going to kind of build this large compound statement piece by piece. So we'll start with the negation. We're going to start with the fact that we need not P. Then we're going to build the Q and not P. And then finally, we'll deal with the entire statement together, P or Q and not P. So first, not P. In order to find this truth table or this column, all we have to do is take the opposite values of P. So that's going to be, since P is true in the first one, we do false, then false for the second, and then true and true. The opposite of what's in the first column for P. Then, if I'm going to do Q and not P, we need to look at the 2 statements involved in that and that is Q and then the not P. So the last 2 columns we written down, Q and the not P. And we're going to do what we did in the previous page with the and. In order for this to be true, both columns have to be true. So the first one is false, because there's a false for not P. The second one is false because they're both false. The third one is true because both columns are true. And the last one is false because of the false in the Q column. And now we're just building piece by piece. So next we're going to look at the total statement that we're looking for, P or Q and not P. And there are two parts, the P and the Q and not P with the or. So we're going to look at the fourth column and the first column here. And then do our or, our disjunction truth table. So in order for the or to be true, there has to be a true in one of the columns, at least one of the columns. So we're looking at only the first and the fourth column here. We're looking for if there's a true in either the column, then our whole thing is true. So we have true, 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 and false in the last one. And this is what we are analyzing, is this last column. So it says, under what conditions is the following statement true? It is always true unless both P and Q are false. That last column we looked at. So that would be if I do not have a high school diploma, I do not have a high school diploma and I do not have a full-time job. All right, let's do it again, this time with three statements. So under what conditions is the following statement true? I own a guitar, and it is not the case that I am a musician or a collector. There are three statements here. P being I own a guitar, Q, I am a musician, R, I am a collector. And if we translate our big compound statement into symbology, we have I own a guitar as P. We have our and symbol. And then it is not the case. That's going to be our not. That I am a musician, which is Q, or I am a collector, which is R. And then it's just a matter of having the parentheses in the right place, because it's not the case that I'm a musician or a collector. It's both of those together. Not just the musician part is negated. So we get our P and not Q or R. And the and refers to both pieces here, this P and the entire thing, not Q or R. So we start with our three simple statements, P, Q, and R, and we need to do all possible combinations. Since there are three simple statements, we have 2 cubed 8 rows. And the way that we do this, we're going to say is, for the first one, our P statement, we're just going to list half of the options are going to be P is true, the other half are false. So we're going to label those as the 4 trues and then the 4 falses. Then within each of those blocks, we're going to do half have Q being true, half have Q being false, half have Q being true, half have Q being false. So we do true, true, false, false, true, true, false, false. And then within each of those blocks, we have half being true for R, half false, true, false, true, false, true, false, true, false. So note that if we had 4 options, so if we had n equals 4, that's 2 to the 4th equals 16 options, we would do our truth table as 8 trues, we'll just list them all here, and then 8 falses. And then in that first block, we would have 4 trues, 4 falses, and we continue. And then in the next block, we would do 2 trues, 2 falses, And then the last block, we would do one true, one false. And that was going to give us a systematic way of getting every single combination there. All right, in this case, we're just doing 3 options. So we have our 8 options there. All right, so first thing we need to do is build Q or R. So we look at the last 2 columns, Q or R. If there's a true in either one of those columns, then our statement here is going to be true. So there is a true in each of the first 3 columns, and then we skip the 4th, 5, 6, 7 there are true, and then it's false in the 4th and the 8th columns. Then we're going to do not Q or R. That is, we're going to take the opposite of what we just found, the negation. So we have trues become falses, falses become trues. And then we look at, finally, P and not Q or R. So we're looking here at the first column and the last column here. And they both have to be true in order for that last column to be true. So we're going to have a false in the first, because there's a false in the first row, and the second row, and the third row. The 4th one is true because they are both true. False, 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 and then false all the way through. So we can say that this is only true if P is true, Q is false, and R is false. We're looking at this 4th row is the only time that it's true. So now let's think about the conditional. This is kind of the weird one, but we'll explain why it's weird. So we have P implies Q. We still need to start with P and Q. And in order to understand this, we're going to look at this simple example. So P could be the statement, you give me $50. Q could be the statement, I give you a ticket to the ballet. So P implies Q is the if-then statement. If you give me $50, then I will give you a ticket to the ballet. So the first 2 are not that complicated. If P is true and Q is true, then the implication is true, and that's pretty straightforward. If P is true, if you give me $50, but Q is false, I do not give you a ticket to the ballet, then the implication doesn't work. One of those parts doesn't work. The consequent, the second part, is not true, so the whole thing is false. But it gets weird when we talk about the antecedent, the first part, not being true. So we can think of conditionals as promises. And it is true, the value of the conditional, so P implies Q, is true if the promise is withheld. We'll say satisfied. So in the first, if P is true and Q is true, the promise is withheld, it's all good. In the second one, it's not withheld because the consequent was not withheld, or not upheld, not withheld, sorry. But if P is false, if you do not give me $50, then it's like the promise doesn't even make sense. This transaction would never even happen in the first place. So therefore, this promise doesn't really even exist. So therefore, we call this true kind of by default. And this is what we call a vacuous truth. A vacuous truth is one in which the antecedent is false. That is, the if part is false. And maybe it's better to think about an even simpler example. Let's do the simple statement: if I watch TV, then I watch The Office. If the antecedent is false, then it's not even true that I didn't watch The Office. The whole concept doesn't even make sense, right? I'm not watching TV, so it doesn't even matter, to talk about what I would watch if I do watch TV. With the $50 in the ballet, if you don't give me $50, then we're not even talking about a ticket. The whole thing doesn't make sense. So it's just true just by default. It's a vacuous truth. All right, so conditional truth table, if they're both true, it's true. If it's true, then false. That's the only time we're going to have false. If the antecedent, the first part, is false, then it's always going to be true, vacuously. So let's do a big truth table using this conditional. Construct a truth table for P or not Q implies R. There are three simple statements there, P, Q, and R. So we have our 8-row truth table organized in our fashion we talked about: 4 trues and 4 falses, 2 trues, 2 falses, 2 trues, 2 falses, and then alternating true, false for R. We're going to first build this P or not Q. That means we have to deal with not Q first. We take the opposite values of our Q column: false, false, true, true, false, false, true, true. Then we look at P or not Q. That is, we are looking at our first and our fourth column. And if there is a true in either one of those, then the whole thing is true. So the first 4 are true just because there's a true in the P column. The next 2 are false because they both have falses, and then the last 2 are true because the not Q is true. And then finally, let's do our conditional. P or not Q implies R. So this is only going to be false if the first part is true, the second part is false, then the whole thing will be false. Otherwise, it's going to be true, either vacuously or just because it's true with the conditional. So let's look for the points where P or not Q, which is our first part here, is going to be true, but our second part is going to be false. So that is going to be everything but the 5th and the 6th columns. These are going to be vacuously true. Because the antecedent is false. We have true in the first, third, and 7th rows because we have true in both of those columns. And then we have false in the other 3 because we have a true in the antecedent and a false in the consequent. And there is our truth table. So now let's think about using everything we've learned to think about equivalent statements. 2 statements are going to be equivalent, 2 compound statements are equivalent if their columns of a truth table are the same in each entry. So we're going to construct a truth table to determine if the following 2 statements are equivalent. That is, if I am a homeowner, then I pay property taxes. And the second one is, I am a homeowner and I do not pay property taxes. Now these are kind of weird because one is a conditional and the other is a conjunction. They're kind of different forms, but we're going to see if they have the same true-false values. So note that we have two statements that we're looking at. I am a homeowner, which is going to be P. And then I pay property taxes, which is going to be our Q. In the second statement, we have not Q. And we combine them in the first with a conditional, if then, and the second with a conjunction, and. All right, so let's look at these. In order to build our two things, we need to have not Q, so let's find that first. Not Q is going to be false, true, false, true, the opposite of the Q column. Now let's look at P and not Q. That's going to be the first and the third column. In order for that to be true, both columns have to be true. So the first one is false because there's a false in the not Q column. Next is true because they're both true. And then the last two are false because there's a false in the P column. Now let's look at P implies Q. That is, we're going to look at the first column and the second column. The first column is the first part, second is the second part. We know that if the second part is false, we get vacuously that these are true. We have that this is true in the first, true in the first and then false in the second. So our question was, look at the last two columns of our truth table and determine if those are the same, if those are equivalent. And in fact, they are definitely not equivalent. In fact, they are opposites. So maybe surprisingly, we get actually a different result here. We actually have that if we negate P implies Q, that's actually the same as P and not Q. So we're going to show this on the next page as well, but this is actually a way that we can negate conditional statements to think about them as a conjunction. And that can be a very useful thing to do. Negating statements is very important. So our question, are these two statements equivalent? No, they're definitely not. But they're actually negations of each other. They are opposites of each other. All right, so now let's talk about De Morgan's laws, and we'll talk about negation in general. So De Morgan's laws are ways to negate conjunctions and disjunctions. And in fact, De Morgan's laws are going to show up later in this course when we talk about set theory as well. And really, De Morgan's laws apply to a large variety of different kind of problems, but they all have to kind of deal with negating conjunctions or disjunctions in the right context. So here, De Morgan's laws tells us how to negate P and Q or P or Q. So if we negate P and Q, we're going to get not P or not Q. And this is like distributing. I like to think about it as we are distributing the not. So we get the not is going to distribute to each of those three parts, the P, the and the Q. That gives us not P, not Q at the end. And then we think about what's the opposite of and. That's going to be or. This isn't exactly what's happening, but it's sort of the basic idea that we're kind of distributing the not to each part of it. So therefore, if we take the negation of P or Q, it's like we're distributing that negative. We have not P, the opposite of or is and not Q. So let's find the negation of the following statements. We have, it is Friday and I receive a paycheck. So this is like our P and Q. So the negation of this will be not P or not Q. So we can write that as it is not Friday, or I don't receive a paycheck. The opposite of the first statement or the opposite of the second statement. All right, let's do it again for an and. We have you are correct is a statement. I am crazy is a statement. We are connecting them with an or. So we take the negation of P or Q. We're looking at not P and not Q. So written in a sentence, this would be you are incorrect, you are not correct, and I am not crazy. All right, so now let's think about just negation in general. Here's a summary of all the negations that we've done so far. We know that if we negate a negation, they cancel each other out. We're left with just where we began with. So not P is just P. Our De Morgan's laws are the next two things here, how to negate a conjunction and a disjunction. And then we have the negation of a conditional, which we just saw on 2 pages before. If I go back, we had this result kind of pop up from our example that not P implies Q is P and not Q. And then we talked about negating statements in general. If you have something that's a universal affirmative, you're talking about all of something, and you negate it, then you're going to say that some things are not. You have a particular negative. So the opposite of the universal gives you the particular. The opposite of the affirmative gives you the negative. And again, you can think about this as distributing that not to each part, and just knowing that the opposite of universal is particular, the opposite of affirmative is negative, and all the way down the line. This is probably the most complex part, is how to deal with the negations, and then the conditionals probably on top of that. We're going to look at the conditionals in a lot more detail in the next video.